Hi, my name is Travis English, and this is how to design a hospital central VAV system, variable air volume system. Here are the learning objectives. Please pause if you'd like to read those. We are moving on. So let's acknowledge that this paper, this is a white paper that we're presenting off of the white paper here. This paper is an offshoot of the California Energy Commission research project, which involved converting constant volume systems in a hospital into variable air volume systems. And the engineer of record and the primary author of that project is our revered colleague and my buddy, Austin Barlin. So we're going to talk through a 7-step process here in the next 10 to 15 minutes. And since we've only got that much time, I'm going to assume that most of you in the audience already know about hospital air system design. From that perspective, step 2, 3, and 4 are things that you're doing already, and we won't belabor those a whole lot. Step 1 does have an added wrinkle, and then step 5 is brand new. Step 6 and 7 could be called optional or advanced. They're only required if you want to do database commissioning or connected commissioning. So basically, if you want a VAV system that works in theory or on paper, then you only need to do up to step 5. But if you actually want to validate the system with data, then you're going to need to do step 6 and step 7. This slide shouldn't be there. All right, so designers actually already know. Step 1 is to define the peak and the neutral conditions. Designers already know how to pick peak conditions, so I won't talk too much about that. So what the heck is a neutral condition? Well, what we're looking for is a pleasant nighttime hour, because at night the internal loads are low, solar loads are 0. So if the outside air is comfortable, then that becomes the point of minimum load on the system. No heating load, no cooling load, minimal load. So the easiest thing to do is to use a generic neutral condition that is 3 a.m., 70 degrees, 40% RH. If you live in a climate where that literally never happens over the course of a year, then obviously my best advice to you is to move. But barring that, you can pour through the weather data and identify the actual minimum load hour the same way that you pour through the weather data and identify the peak hour. So if you're wondering, why should I care about the neutral hour? Why should I care about the neutral condition? Here's why. For any central hospital air system with any set of options in any climate, the annual energy demand of that system is a function of the supply air quantity at the neutral condition. This figure here shows a generic model based on Sacramento, California. You can run your own models in any climate with any set of options. In general, an air handling system with 4 air changes per hour, or 0.6 CFM a square foot, has an annual energy demand that's about double the same system with 2 air changes per hour, or 0.3 CFM a square foot at neutral. As a very, very general rule of thumb, that green bar that's going across these, if you want to get down to about 100 or 150 EUI energy target, then you want to get down to about 0.4 or 0.5 CFM per square foot, which is in the neighborhood of 2.5 to 3 air changes for the full volume of the system. That's where you should be landing at 3 a.m. and 70 degrees. So steps 2, 3, and 4, dividing the space into zones and load calcs and peak condition RBSs, these are common practice. Hospital engineers are required to do this on every job already. The result of those steps is this room balance schedule, which you would find on any set of hospital plans. There is kind of an extra level of detail if you want to do VAV. If you want to do VAV for every zone, you need to identify what is happening there at 3 in the morning. Can that zone be shut off entirely? Can it be turned down? Does it have to run at 3 a.m.? So you have to go through this kind of exercise. This one is kind of nice and was color-coded. So some do's and don'ts during the load calcs and the peak load establishments. First one, for plug and process loads, look at the published studies out there from running hospitals. That data exists, and so really it should be used. I know that most firms are probably still estimating plug loads and equipment loads, based on nameplates or diversity factors. If that's what you're doing, please consider stopping that and use the published data instead. Same goes for lighting. There's a lot of data out there on lighting energy use in hospitals in the actual conditions. So please don't use design data or installed watts or diversity factors or things like that. Use the real data. The real data is actually lower than what you'll come up with just by doing a diversity factor. And then, of course, occupant loads are the last area of that. Occupant loads are a pretty significant source of error in load calculations. Obviously, our rooms need to accommodate the peak number of occupants in that room. But if you have 5 nurses and 3 doctors, they can't be in 20 patient rooms at the same time while they're also in the break room and also in the nurses station. So the overall peak occupant density in a hospital is going to be about 300 to 400 square foot per person. And a good way to think about that is to count the number of parking spaces. If you assume that every single space is taken, then you can't, if you drove to the hospital, you wouldn't be able to find the space. And every car that's parked there could have 1.2 people per car, then that is about what you'll get. That is absolute peak occupancy. If you're a design engineer, you might want to pause and jot down the numbers down at the bottom of the screen. In preparing this design guide, we actually audited about 750,000 square foot of projects in design by different design firms to look at norms and outliers. I'm going to show some of that data a little later, but those ranges might be useful to you. So that brings us to step 5. As I mentioned, this is new. Our design engineers are very used to completing these room balance schedule for the peak load conditions. So every design firm that does hospital design has a version of a spreadsheet that looks something like the right side, or I'm sorry, the left side of this page here. It has supply and return and outside and pressurization balances for every room in the system. But for VAV systems, you actually need to do a full second and sometimes third set of calculations. You need to do one at the daytime minimum, and then you also need to do one most of the time at the nighttime minimum. So you select the neutral condition from those room by room. And if this looks like a laborious and time-consuming process, then you're correct. You are understanding correctly. It is, though, totally incorrect to assume that each room and each zone will turn down properly without this type of planning, because there are rooms in the system that have pressure relationships, positive and negative pressure relationships. So you've got to plan for those to be true at the peak and at the neutral and at the overnight condition. So let's take a look at that data that I mentioned before. We, during the year 2019, we audited 750,000 square foot, 9 air handling system projects in design from different design engineers, and use that data to sort of take a look at what was happening during design. First off, you can see the fraction of area that the space types take up. Corridors and offices are the most common spaces in hospitals. It kind of hands down. So those spaces have a lot of opportunity for turndown. We found the average peak design supply at, you see, like 5 and 9 air changes, which means there's a legitimate 60 to 80% opportunity for turndown during the day, and in the offices even more at night. Patient rooms and storage rooms and toilet rooms round out the top 5. Patient rooms we found frequently designed at about triple the minimum, so there's a 60% opportunity for turndown. Toilet room or storage rooms can actually be shut off when they're unoccupied. And then toilet rooms also can be turned down or shut off when they're unoccupied, although we haven't seen any designs that actually do that. What you can see here is that just in the top 5, there's a big opportunity for turndown to the code minimum. So the opportunity is quite big. Here's a second page of that data where you can see some of the more regulated spaces. You'll see operating rooms on this page and isolation rooms on this page. I want you to notice first and foremost that those spaces make up a very small fraction of the total areas of a hospital. So even though they have high code requirements and their overall impact on turndown and overall impact on system CFM is pretty small. Based on the set of data and kind of a code analysis of that set of data, we can look at some of the checksums for the neutral condition or the code minimum condition. So your occupancy should be somewhere between 500 and 1,000 square foot. That's even lower than it was during the day. Total system supply air, as we mentioned before, should be able to turn down to about 0.35 to a half a CFM per square foot. The outside air and the exhaust air are going to wind up, you need to balance them out with each other. And so I think in most cases, you wind up at about 0.2 or 0.25 CFM per square foot to achieve that balance. Okay, so here's step 6 and step 7. I said that these are optional or advanced. So if you want a VAV system that works on paper or works in theory, then you don't have to do this. But if you want a VAV system that works in a building in reality, then you better check it. It's kind of a funny story. A couple of years ago, I was having dinner with another mechanical engineer and then an electrical engineer, and we were talking about ventilation and hospital energy. And the electrical engineer says to us, he says, hey, well, you guys know, right? For any time of day and outdoor air temperature, you guys know what the CFM is supposed to be in the system or in the building, right? And we both looked at each other kind of with embarrassed looks on our face, and we said, well, no, actually, we don't. We never do calculations at that level of granularity or that level of detail. Turns out that is actually what you need to do. In order to commission a system and make sure that these things are working correctly, the design engineer must be able to answer numerically, given the time, the day of the year, the time of the day, and the outside air temperature and the outside air humidity, if that's a variable, what are the high and low expectations of system airflow? And you need to know that so that you can test it. It's a little bit harder than it sounds. First off, make sure that you can measure CFM or fan KW if you can't measure CFM. If you miss that in design, you're screwed. But pretty literally, once the system is up and running, you let it run in automatic for at least 5 days, and you confirm that the system is turning down according to the design intent. In particular, you want to confirm that overnight turndown and make sure that your systems are actually ramping down to what they were supposed to do during design. And while this seems like a very simplistic thing, hey, let's make sure that the variable air volume system does in fact vary the volume of air. If you've never done it, then just a word to the wise, don't get too depressed when you see your first set of results and everything looks wrong. Rest assured that's normal, and it takes some trial and error to get these systems to actually work according to their design intent. If you're doing database commissioning, that concept goes quite a bit further. So you actually need to put acceptance criteria for everything that you want to be successful into your control specs. Acceptance criteria look something like this, what you've seen on this page. So you can jot down some notes if you want to. You need to actually state the high and low acceptable values and the acceptable deviation in the data. And you've got to put that in the specs along with all the points that you need to do the validation. And then, of course, you need to have nerves of steel. Because if the data doesn't match the acceptance criteria and those acceptance criteria are in the specs, then you need to fail the job and not pay the contractor and not award substantial completion and hold everybody to account until you actually have a building that's functioning correctly according to its design intent. We've outlined a process here to design variable air volume systems for healthcare applications. There's 7 steps. You see the 7 steps there. As we said, steps 2, 3, and 4 are relatively normal. People are doing them now. Steps 1 has a new wrinkle of identifying that neutral condition, and then step 5 is entirely new, which is to do a full set of calcs at that neutral condition. Step 6 and 7, you don't need to. If you're fine with having a VAV system that works on paper and in theory, then you don't need to do step 6 and 7. But if you want a VAV system that works in a building in reality, then you probably should. I don't know if my reputation precedes me with the audience or not, so I'll go ahead and say it. I do have a history of being critical of code ventilation rates. I believe a lot of them are arbitrary and historical carryovers, which are wasteful and don't actually provide value. But that's really not important right now. The biggest gap that we see in energy and performance is in the design engineering community. Design engineers are not designing systems to reduce air down to those code minimums. I've said before that if we were to leave the lights running in all the office spaces overnight, then we would all be shot or laughed at the very most. But it's extremely common for hospital design engineers to run the HVAC systems at full blast in admin spaces, in clinical spaces. You just run it all night, all the time. And so we have to stop that practice. And that's the biggest gap that we see right now, is in the design engineering community actually designing to and achieving those levels of turndown. Now, that's not to say that the code minimums are something that we shouldn't be critical of. We should be critical of the code minimum systems. And if our design community actually succeeds in turning down to the levels that we could be, then we should be having a conversation about codes, and in about 10 years that'll sort of manifest itself. But right now, the biggest thing is to design a VAV system that actually has the turndowns in it and then actually gets there. If you want to see this in white paper form, it is going to be in ASHRAE transactions. As I mentioned in the beginning, this is also a part of that California Energy Commission project. So a similar white paper appendix will be published there. And I don't know how we're handling questions during the virtual conference, but this is my email number. And please feel free to reach out to me at any point. Thanks.